technical aspect of quantum theory, in the sense that we talked about the mathematical backdrop, that is the linear algebra backdrop of quantum theory. Now, in continuation to that, we are now going to get into the tits and bits and of elementary quantum physics. So before going into the technicality of it, so let me just first introduce what is quantum mechanics, how it came to be, with some historical introductions. So yeah. So quantum theory is what? Quantum theory is a description of the way the small particles behave that make up the universe. So small particle means I'm talking about at an atomic scale. So I'm talking about electron, protons and neutrons and all these. So it has been observed in the early 20th century, or we can say very late 19th century, that the subatomic particle, subatomic was not discovered at that time. People are discovering that atom is also can be divisible. Atom can be broken up into tiny particles like proton, neutron and electron and all that. And at that time, experiment shows us that it behaves curiously. Its behavior is different from how we understood physics at that time. So as a historical introduction, we can say that at the advent of 20th century, so the after industrial revolution, after the steam engine and machines and all that, so we were, human civilization were advancing in technology in leaps and bounds. And also at that time, from the perspective of theory of physics, at that time it was somewhat, we can say, complete. So the classical physics that we know today was somewhat got into the complete shape that we perceive today, that we read or teach or today. So it was more or less constructed. So people thought that classical mechanics was constructed and established thoroughly. So was the theory of electricity, that is electrostatics, magnetostatics and electrodynamics also. So in Maxwell, the famous physicist Maxwell culminated all the theories of electricity, magnetism, and also understood that electromagnetic theory, that light is also connected to that. So that is also more or less completely developed. And the theory of statistical mechanics was also there at that time. So people thought that we know sort of everything about physics that can be known at that time. Also, understandably so, on that time also the industrial revolution happened and technology was advancing in leaps and bounces. So we, at that time, we also discovered very strong devices also to observe more closely. So then when we have using those technology and all that, at the time we understood that no, we don't know everything about physics, because then we discovered that atom, which was at that time understood as the smallest possible, the unit of all matter, so it cannot be divided more, it is indestructible and indivisible. But at that time we understood through various experiments that no, atom is also divisible, and it is divided into much tinier particles like electron, protons and neutrons. So I'm not going to talk about that, but then when experiments happened, it was shown that the behavior of those tiny particles or behavior of those subatomic region, the universe of subatom. So if we consider atom to be a very tiny universe, So the physics of that small universe is completely different from the physics of the classical physics that we understood by observing the nature around us. So quantum theory, the experiment at that time was quite counterintuitive. So these are the physicists that we give the credit for the development of quantum theory. These are Max Planck from the top, we can say. This is Max Planck, and all of you know Albert Einstein, and then Niels Bohr, Louis de Broglie, Max Born, Paul Dirac, Warren Heisenberg, Wolfgang Pauli, Erwin Schrodinger, and Richard Feynman. There are also others. We have missed many others in this. So these are the most prominent faces when we think about quantum physics. So it all started from Max Planck and Albert Einstein, and then these guys, along with many others, other brilliant physicists or scientists, developed the quantum theory. So the time of discovery of quantum theory, two separate, completely new theories were being developed. One is this theory of subatomic particle, or the subatomic universe, I can say, and another is the theory of the cosmological scale, huge scales. So we are talking about galaxies and stars and all that. So basically, we two theories are, one is this theory of quantum mechanics, another is the theory of relativity. So we know Einstein, probably the most, or at least the one of the three most famous physicists of all time, in fact. So Einstein, who is also sort of established himself not only in the domain of science but outside society in general. So he was the one who discovered relativity, who established the theory of, first the special theory of relativity in 1905, and then 1914, around that this general theory of relativity came. So these the theories laid the foundation of the modern physics and cosmology. So, but we are not going to talk about relativity, we are going to talk about quantum mechanics. So in the early 17th century, when Newton was the sort of, the father of modern day physics, the physics in general that we know, the subject, the branch of knowledge that we know as physics, Newton was probably the father of that. So he gave us the theory of mechanics, the spectrum. So we know that light can be divided into 7 main colors. My connection is stable, I guess.
Sir, your connection is still stable, and but your voice is little breaking.
Voice is little breaking. Just a minute. Now?
Yeah, now it's fine, sir.
Yeah. Okay. So voice is a little breaking because I just saw a message here that the connection is unstable. Anyway, fine. So if there is any problem, please notify me.
Sure, sir.
Yeah. So he said that light is made up of tiny particles. Later we named the particle as photons. So these were just after coming up with the laws of motion and gravitation, and when he developed calculus also. So, but after that, during 18th century, most scientists accepted that light is not made of a particle. Newton was wrong in that case. So people like Huygens, Hooke, and also Young, they developed the theory, and also they experimentally demonstrated that light is basically a wave. Because probably some of you or most of you have heard of or read of the Young's double slit experiment, where interference pattern was established and shown that light, shows this kind of behavior. Interference pattern is a property of wave. So along with this experiment and with many others, that it was firmly established was light is not a particle, collection of particles. It is a wave. Later we understood that it is an electromagnetic wave. And after Maxwell, we understood that it is also connected with electricity and magnetism, where Maxwell sort of culminated all of them in a single grand theory, that is the theory of electrodynamics. So I'm talking about Thomas Young, who gave this interference experiment, then after that diffraction and all that. But in 1905, so Einstein produced a paper on something called photoelectric effect, showing that light really was made of particles. So what is this photoelectric effect? That there are some metals, if you light it up, then electrons are dislodged from those metals, crudely speaking. So what should happen? That usually from the wave theory we understood that energy is associated with the square of the magnitude of a wave. So basically it is proportional to intensity, and intensity is proportional to the modulo square, or the magnitude square, amplitude square. So it is proportional to the square of the amplitude, or the magnitude square of the magnitude of the amplitude, technically speaking. But so the intense the light will be, so according to that, it is expected that as the light that we are using is more and more intense, so more and more electrons should be dislodged. But it is curiously, it was not so. Even very less intense light of a certain frequency, if that is used, then electron dislodged from the surface of the metal. But if we use something of a different or lower frequency, and how much intense light we use, electrons are not dislodged. So this is a very curious example from the perspective of the physics we understood at that time, because this is not matching to our theory. So Einstein then said that no, Einstein used a principle called this one, which is this energy is proportional to the frequency. So this is called Planck's law, and this constant H is called Planck's constant. It is one of the universal constants. So just like gravitational constant, the capital G, not the gravitational acceleration, the gravitational constant capital G, mass of an electron, this H, these are universal constant, or the velocity of light or the speed of light in vacuum. These are universal constant. So this H, this Planck's constant, is also a universal constant. So Einstein used this Planck's law and said that no, the energy is, I am believing in Planck, and the energy is proportional to frequency. So as I am saying here, it was expected that once the brightness of light is reached a certain level, electron would be dislodged. We found that the brightness made no difference. What mattered was the color, that is which is associated with frequency, or wavelength or frequency. So Einstein said that no, it is energy of those, the light we are using is proportional to frequency. So light is understood is made up as a collection of particles of different color, just as Newton suggested. Einstein called them photons. So blue colors have shorter wavelengths and therefore higher frequencies and higher energies. Like ultraviolet is more than that, and there are more higher frequencies than that also. So the energy of photon was proportional to the frequency. This E equals to hf, which is the Planck's theory, Planck's law. This h is called the Planck's constant. So using this theory, Einstein had successfully explained the photoelectric effect, which was at the time a very big discovery. So although Einstein has produced revolutionary theories like special theory of relativity, general theory of relativity, he also worked in Brownian motion. Einstein got his Nobel Prize for explaining the photoelectric effect. So see, a red photon did not have enough energy to dislodge an electron, and no intensity of red light, coming back to this photoelectric effect we are discussing here. So dislodge an electron and no intensity of red light would do the job. However, a single blue photon did have enough energy to dislodge the electron. This showed that the energy of light came in discrete packets called quanta, or this sort of validates the assumption or the hypothesis of Newton that light is made up of particles. Now we are at a very tricky position. In the 18th and 19th century, 17th and 18th century rather, that it has been firmly established that light is a wave. There is no denying those experimental results. If you repeat them, you will find the same results, that it is firmly established that light is wave. But here also, when we are explaining something like photoelectric effect, or rather there are other examples like that also, Compton effect and all that, where we understood that is also firmly establishes that no, light is a particle. So light is also a wave, it is also a particle. So this is something which was very curious at that time. So now it is seen that light was both wave and a particle. Eddington, there was a physicist named Eddington who suggested calling it a wavicle. So anyway, so it is now well accepted that photons behave in some ways as wave and in other ways as particles. Similarly, also, it has been shown that electrons, which was primarily understood as particles, they also have wave nature. So all this started, this explanation of these curious experiments started from Max Planck, who gave us this result of E equals to h nu or hf, whatever. So energy is proportional to, so he was doing this to explain the theory of radiation. So the energy is proportional to frequency, and therefore there is a proportionality constant is needed. That constant is called Planck's constant, which is a universal constant. Later, in 1913, Niels Bohr came up with the model of hydrogen atom. So here also you have all of us, even we have read it in our school days about the Rutherford's model of atom, how it was unstable. Though it was in the correct path, but it was not fully developed. Niels Bohr did that and said that hydrogen atom, and explained the stability of hydrogen atom. So what is the stability? So the Rutherford model was that the nucleus consisting all the positive charges, that is proton, and the masses, that is protons and neutrons, and electrons are revolving around them. So charged particle in a circular path means its velocity is changing, since direction is changing always. So basically it is under acceleration. So it is we know that previously, which was also a correct theory, is we know that the accelerated charge radiates energy. So now the point is, if electron is always revolving around the nucleus, so it is radiating the energy. So ultimately one time it will lose all of its energies, and then it will collapse over the nucleus. So it has been calculated at that time that, so using this we can see that atoms cannot be stable for even for some seconds or something like that. So how can then hydrogen atoms or any atoms are a stable structure? So Niels Bohr said that no, when this is also something that cannot be explained by classical mechanics, when the electrons revolve around the nucleus, they do not radiate energy. So these, and however, so these the radiuses with which these paths of electrons are not just any path. So there are some fixed levels or fixed particular levels in which these electrons can revolve around. So when they revolve around these in this particular path or particular level, they do not radiate energy or they do not absorb energy. Only when they jump from one orbit to the next orbit, they either radiate or accumulate energy. That is, so these, as this picture goes, these orbits are given by the level n equals to 1, 2, 3 and all that. So when some electron jumps from lower level to higher level, it acquires energy and go to the higher energy level, and from higher to lower it radiates energy and goes to lower level. So these are what are these paths? So the paths are given by the Bohr quantization model, so which is associated with its angular momentum. So that is again another curious example where we are not obeying the classical laws. So these, whatever these laws, for Newton's Planck's law, where the quantized energy, and then the Niels Bohr who quantized angular momentum. So these are separate laws, but which explain the particular phenomena, just like Planck's law. By using that, Planck explained the radiation theory of radiation, and Niels Bohr explained the stability of hydrogen atom, just like Einstein also explained the photoelectric effect. So there are some discrete particular words associated with some explanation of some particular phenomena. So there are some other these kind of phenomena are also happening at that time. So then people understood that we need a new theory. We have to accumulate all these new knowledge that we are gathering as a separate laws, as a different quantization laws. So we have to gather them and build a new theory, because it is now sort of understood that classical mechanics, the physics we knew at that time, will not be able to explain this universe of atom. So we need a new theory. Then came this new theory is the theory of quantum mechanics that came at that time. So what are the phenomena which classical mechanics failed to explain? There are many, but these are only few of them. One is the stability of atom, which was explained by Niels Bohr, spectral series of hydrogen atom, black body radiation, also photoelectric effect and all that. So we say that with Max Planck, who gave the energy quantization rule, is the advent or the start of quantum mechanics or quantum theory. So in one way we can say that it is a generalization of classical physics that includes classical laws as a special case. Quantum physics extends the range to the region of small dimension, just as c is the velocity of light signifies universe as an universal constant, this Planck's constant h is also, which characterize quantum physics, is also another universal constant. So quantum mechanics was able to explain photoelectric effect, black body radiation, Compton effect, emission of line spectra, and all that. So I have already discussed these things. So let us move on to something called wave particle duality. We also discussed it earlier, that we have seen at that time that, for example, light, which can behave both like a particle and a wave. So, and also we have seen some other experiment, that's electron, which can also behave like both particle and a wave. So we came to a conclusion at that time. So there is a duality between these wave and particles. Matter has both of these properties ingrained in them. They have a particle property, or also all of them have these wave properties. So that is the wave particle duality. So de Broglie gave the concept of something called matter wave. He said that a moving particle, whatever its nature, it is always associated with a wave which is called matter wave. So and then gave a law for that also, or how he gave that. So this is the energy of a photon is, you see that this is the E equals to E h nu. This is the Planck's law we know, and we know this famous, probably the most famous equation in physics, which is this E equals to mc square. That is also we know. So c is of course the speed of light. Here E is energy. Nu is the frequency. So if we just both equate them both, we have what? Mc square equals to h nu. So if we adjust a little, we will find h nu means nu is frequency. Frequency can be understood as velocity, I mean speed, that is c, by wavelength, that is lambda. So mc square is therefore hc by lambda, which gives us lambda is equals to h by mc. Now mc means basically the mass into velocity, mass into speed, so basically, or velocity, so that is basically the momentum of the particle. So here we have the wavelength lambda, which is equals to h by p. P is what? P is momentum. So lambda, which is a property of wave, is now connected by this de Broglie's hypothesis with the momentum of a, which is a property of a particle or a body. So this lambda is the wavelength associated with this matter wave. Now you see, I say the particle has to have a velocity. So if it does not have a velocity, it is relative to some frame. So if it is say it is static, then the momentum should be zero. Then this lambda is very big. In fact, it's infinity. So that means frequency is tending to zero. So waves are, so therefore waves can only be associated with moving particles. Only then we can have a finite lambda, that is a finite wavelength of that. So now you see, if we are considering very heavy particles, so why we cannot realize this lambda? So this is this matter wave for in everyday life. So there are bodies moving always, the cars and all that, cars and aeroplanes and people also, and everything. Why cannot we realize those matter wave in this classical situation? Because you see, so these big bodies or macroscopic bodies, they have considerable mass. So the denominator, we have this momentum quantity is very big. So which gives us, so associated lambda is so small that we cannot understand it, or we cannot realize it. But only for subatomic particles, which are minuscule, whose masses are very small, just like electrons, say, it's of the order of 10 to the power minus 31 kg. And so protons and neutrons are bigger than that, but it is also of the order of 10 to the power 19 or something. So they are, sorry, 10 to the power 27 or minus 27 or something. So they are very small. So only for those particles, this lambda this matter wave can be realized, not for macroscopic bodies like us, or the cars or aeroplanes or all that. So then another very important principle which I was talking about in the previous day is this Heisenberg's uncertainty principle. We'll talk about the technical aspect of it later. This is just an introduction. So Heisenberg said that this is another curious property of this quantum or subatomic particles, that position and momentum, which basically the knowledge of which give us the state of motion of a particle. Knowing the position and momentum of a particle is knowing its state of motion. We know everything about that classically. But quantum mechanically, we cannot measure position and momentum accurately simultaneously. So it is impossible to measure both position and momentum simultaneously with unlimited or precision, with extreme accuracy. So let's say del x, which is the uncertainty in measurement of position, and del px is the uncertainty in measurement of momentum. Then Heisenberg said that they follow this rule that this del x into del px should be greater than equals to h bar by 2, where h bar is h, which is the Planck's constant, by twice pi. So you see, del x is therefore del h bar by 2 del px. So if we are measuring momentum precisely, so its uncertainty will be 0, so del px will be 0. Therefore, del x is infinity. So its uncertainty in position is infinity. Infinity uncertainty in position means we cannot at all know the position of that particle. So this is the very short and good introduction of Heisenberg's uncertainty principle. So this uncertainty principle also extends to other variables like angular position and associated momentum, that is angular momentum. It is also, there is a energy time uncertainty relation, that is time uncertainty and energy uncertainty also. So they also hold these uncertainty relations. So then comes this thing. So now we know some fundamental basic laws has been now established. That is this Planck's law, by which we know E equals to h nu. Now E equals to h nu and E equals to this h bar omega is the same, because h bar is h by twice pi. So here omega is twice pi into nu, that is twice pi into frequency. We know that that is called the angular frequency. So this is the same basically. So E equals to h bar nu, this is the Planck's law, and is P equals to h bar k is from the de Broglie hypothesis. You see, the de Broglie hypothesis was what? Lambda equals to h by p, or p equals to h by lambda. Now h means twice pi h bar, so it is lambda, or p is equals to h bar into twice pi by lambda. Since twice pi by lambda is understood as the wave vector, this k. So this is basically from the de Broglie's hypothesis. So these are the new things that we have understood here. Energy associated with frequency, momentum associated with wavelength or wave number. So now we need an equation. So just like in classical physics, we have the Newton's equation, or after that we have the Lagrange's equation or Hamilton's canonical equation to describe the motion of a particle. So how its state of the motion evolves under what rule. So that is governed by the Newton's laws and the corresponding equation of motion. So we need also here we need an equation of motion for that. So let us first, if we try this associated the state of the motion of the quantum particle with this wave function xi. So this generalization of this wave function is the Kate vector that we are talking about in the previous class. We will again talk about this after a few minutes. So right now understand it as a wave function xi, which we understand as this e to the power j. This is j means this imaginary j, that is root over -1 omega t minus kx x. So this we get from the usual wave equation, wave function. This is how wave functions are understood previously from the theory of wave. The new thing is this omega is not now associated with energy. Omega is h by e by h bar, and this k is associated with momentum, that is p by h bar. So you see, if you take the partial derivative of xi with respect to time, we have this j omega or I omega xi. Now h bar omega is E, that is energy. So E over h, if we want to measure the energy of this wave function, that is basically h bar omega. So that is sort of, this is an eigenvalue equation then. So D is the operator acting on the wave function xi, getting the eigenvalue h bar omega xi. So this I h bar or minus j h bar del t is an operator for energy. So if you want to know the energy of this wave function xi associated with some quantum particle, so then we have to use this operator minus j h bar del t over this wave function, theoretically. Similarly, momentum can be understood in one dimension as this I h bar del x operator. If we generalize this, so here we see that E equals to E is this one, and momentum of this is j h bar del x. So if we consider the particle has the energy, is a free particle, that is, it has only kinetic energy, so it is not under the influence of any force or therefore any potential, so there is no potential energy present. So the total energy is basically the kinetic energy. Kinetic energy can be written as this p square by twice m. So P, the operator of P in this one dimension is this j h bar or I h bar del x. So therefore we can get the P square from it also, which will give us minus h bar square del 2 del x square. Similarly, E operator we already know, so we use it and we find this equation minus I h bar del t over xi equals to minus h bar square by twice m del 2 del xi del x square. So this is one sort of equation that explains, that can govern the quantum particle associated with the wave function xi. So this is the one-dimensional Schrodinger wave equation for a free particle. So if we now generalize this to a concept of a more general concept where we have a potential associated also. So for one dimension, this equation is given by the equation, the box equation in the box we represent here. So if it is also the first term is the energy term, this term is the kinetic energy term, and this V term is the potential energy term. So this Vx or this kinetic energy, this del 2 del x square, they are basically operators acting over the wave function psi. This is generalized in the matrix or the vector mechanics that we explained in the previous session, and we will explain again. We will take that again. So these are the Hermitian operators we are talking about that gives us the observable, because the potential energy, kinetic energy, total energy, momentum, these are observable. These are the properties that can be observed experimentally also. So they are usually associated with some Hermitian operators. So all these operators which are associated with some observables are Hermitian operators. So if we generalize it to 3-dimension, so this is the equation that is the general 3-dimensional Schrodinger equation, named after the famous physicist Erwin Schrodinger, who first discovered this equation. So there is the time dependent part. We are not going to discuss this technicality more here, because we will discuss it in the vector notation that we introduced in the previous class through linear algebra. But I am not going to get into wave mechanics much. So this is the Schrodinger equation. The term is here. It is. You can see which is the kinetic energy term, which is the potential energy term, and all that. And what is the explanation of this wave function here? And in our linear algebra notation, this is the vector, this is the Ket vector. What is that? So that is associated with the probability of the particle, probability of finding the particle. If it is a function of x, that is this xi phi is a function of x, that is position, then this mod xi square is basically here is a typo, dx will not be present here. The position of finding the particle at a particular position x. So the xi describes the properties of a given particle. It's a complex function, it's general. What is the meaning of this wave function? So this quantity mod xi square is understood as the probability. It is Born, famous physicist Max Born gave this interpretation. So it is somehow called Born rule also. So this is the interpretation of this wave function xi. So what are the basic things that we sort of introduced in this very crude and elementary introduction, or a historical introduction of quantum mechanics? That the scientist, the method that we just talked about, the theory that is understood as the Copenhagen interpretation of quantum mechanics, because Copenhagen was sort of the center where all of these physicists gathered around and discovered these, ingenious things. So that's why it is called as Copenhagen interpretation of quantum mechanics. So a system is completely described by the wave function xi, representing an observer's subjective knowledge of the system. So in our vector notation, this wave function xi is replaced by the Ket vector xi. So the description of nature is essentially probabilistic, with the probability of an event to the square of the amplitude of the wave function is related to it. So in our notation, it is as we have understood the norm of it. So that is the inner product of a Ket vector with itself. That gives us the probability. It is not possible to know the value of all properties of the system at the same time, which is this Heisenberg's uncertainty principle. That is, if we know position, we cannot know certainty, then we cannot know momentum at all. But at the expense of some accuracy, both can be measured simultaneously, but not accurately. So the matter, so there is a matter, there is a wave particle, matter exhibits a wave particle duality. So that is every property, every matter has a property, both the property of a particle and also wave. So every such body, moving body is associated with a wave called matter wave, which is explained in de Broglie hypothesis. So if some experiment, okay, so now measuring devices, what is that? So the measurements or the observables, so which gives us the classically understandable properties of a quantum particle, like momentum, like position, like energy. These are associated with operators. These operators are Hermitian operators. So a quantum mechanical description of lab system will closely approximate the classical description. Why? Because there is a we can approximate a quantum mechanical system to a classical one. For example, if we consider this uncertainty principle, so this multiplication of the uncertainties of position and momentum is always greater than equals to h bar. So this h, or the Planck's constant, is the thing that determines this. Now, if this h is tending to 0 somehow, see, so then this multiplication will be tending to 0, then everything reduces down to classical physics. So if you, some of you are interested in quantum, say quantum information and all that, if you study it for long time, then you will, in the more mature study of quantum theory, will show you. So there is a something called decoherence. That is, the quantum particles are very minuscule, tiny particles. So if it is subjected to too much noise or environmental interaction, it's quantum. I am very crudely saying this, so it is technically, what I am saying is technically not correct. But for better understanding, I'm saying this way. So it loses its quantumness and becomes a classical, behaves like a classical particle. So there is a transition from quantum to classical happens. This is called decoherence. We can say this transition as a process of decoherence. So classical mechanics is sort of a special case of quantum mechanics. So in generally, everything around us behaves quantum mechanically, but it's just like as we explained for the matter wave, it is so minuscule, so negligible that we cannot understand it or cannot observe it in any case. So in the limit, there is a classical limit to quantum theory. That is one of that I'm told you. I just told you this is h tending to 0 is one such limit. Where classical mechanics, we can get back the classical mechanics from the quantum theory. So I'm not going describing this. So basically, this is something for wave mechanical description, which I am not going to talk about. So before going into more technical aspect, so if somebody is interested, so these are the books that I prefer. There are numerous number of quantum books in quantum mechanics. So I am not saying that these are better than the others. There are equally good quantum mechanics books, other quantum mechanics books present, but somehow I prefer these books. That is my personal choice. So this is one is this quantum mechanics by Claude Cohen-Tanouji. It's a sort of treatise or Bible in quantum mechanics, we can say. So it's in 2 volumes, and there is one particular book that I like very much from my graduation days. This is the book called Modern Quantum Mechanics by J.J. Sakurai. So please be careful. There is another quantum mechanics book by Sakurai, which is called Advanced Quantum Mechanics. Not that. This is the Modern Quantum Mechanics by J.J. Sakurai, or the Principal of Quantum Mechanics by R. Shankar. And people who are interested in quantum information, So there is a lecture note which is closer to a lecture note on quantum information, which is readily available in internet. You can find it. It's in lecture notes on quantum information by John Preskill. Okay, so now I'm going to move into some technical description which is associated with the mathematical backdrop I discussed in Tuesday's session. So if anybody has any questions, I can take it now.
Sir, I hope the questions are already posted in your Zoom message box.
So let me just, chats, right? Chat box.
Sir. Yes, in a Zoom chat box.
Okay, I got it. So good morning, sir. This is Shaujan from Secunderabad. So my question is, are there any particles exist between electron and proton? So between electron, what do you mean, Shaujan? What do you mean by between electron and proton? I don't understand. But yeah, so there are other particles like electron. As I understand your question, I can say that there are other particles like quantum electron and proton. They also constitute the subatomic particles. Neutron is one such thing. So there are other particles. You have probably heard of neutrino or something like that. You know of this experiment that is going on, that has been gone. This CERN experiment for these Higgs boson kind of things. So these are only 1, 2 bosons. It's not Higgs boson is not one particle. There are many such. So there are many such particles like electrons, protons, neutrons are present, even tinier than them. For example, neutrino is even smaller than them, supposed to be. So there is nothing in between. I don't know. It is what do you understand? What do you mean by in between proton and electron? But there are other particles like them, like proton or electron. So there is another question is by Manosa from Nizamabad. So my question is, why quantum computing is important in present technology? Okay, so it is many subjective question. So there are many reasons. One is that the computer, quantum computing, you can from the phrase you can know that it is something related to computation. So therefore it is something related to computers. So the computers that we have in present day are classical computers. That is, the machine behaves in a classical way. Yeah, so underlying, of course, when you're talking about the diodes and transistors and their underlying mechanism, there is always quantum mechanics. So that is everywhere, because quantum mechanics is the basic of all interactions and everything. But the computer itself behaves classically. They obeys classical laws. But if we can produce some computers which are very tiny, we know that as our technology improved, the computers that we know, they are getting tinier and tinier. For example, now you have these mobiles and all these, they are, the smaller and smaller of such devices are being made. So if we can make the computer so tiny that it obeys quantum mechanics, then we have certain advantages. There are certain situations or certain computation is mainly done for computing. The main work of computer is computing. So for example, it can solve certain problems much more efficiently than classical, the best possible classical computer or supercomputer can do. So that is probably the main reason quantum computing is so important in present technology. So people are hoping that in next 50 years or not even 50 years, much less than that, we will have a much better computing system, computers, which are these quantum computers. but building such computers is not so easy. That I was just talking about this something called this decoherence or something, where quantum particles loses their quantumness or the quantum property due to environmental interaction. So a sustainable system, so you need, if to build a quantum computer, is has to be sustainable also. Just like our laptop, from the laptop I'm talking to you guys, or from the laptop or from the computer, you are hearing these or something. So they are stable system. So to make a stable quantum computer, that is the main technical challenge that we face today. So for this reason and many more, quantum computing is one of the most important future technology or current research, one of the most questions. That's why I was okay. So I think there are no other questions. So shall I take a? I mean, I need to have some water. So shall I take a 2-minute break and start?
No problem, sir. You can take 5 minutes break and then.
First question starts now. Which planet in our solar system is known as the red planet? Option A, Jupiter. Option B, Mars. Option C, Venus. Option D, Mercury. Your time starts now. The correct answer is option B, Mars. Mars is the fourth planet from the Sun and is considered as the red planet. This is due to the high iron content in its soil, which imparts a red color to the soil. Second question. In which country white elephant is found? Option A, Thailand. Option B, Myanmar. Option C, Cambodia. Option D, Malaysia. Your time starts now. The correct answer is option A, Thailand. Thailand is known as the land of white elephant. White elephant are not a distinct species, but rather elephants with unusually light skin. In Thai culture, white elephants in the king's possession represent the power and prosperity of his reign. Third question. When is National Youth Day celebrated in India? Option A, January 9th. Option B, January 16th. Option C, January 10th. Option D, January 12th. Your time starts now. The correct answer is option D, January 12th. India celebrates National Youth Day on January 12th. This date was chosen to honor the birthday of Swami Vivekananda, one of India's greatest spiritual and social leaders. In 1984, the Government of India declared January 12th as a National Youth Day, and since 1985, the event has been celebrated in India every year. The government quoted that the philosophy of Swami and the ideals for which he lived and worked could be a great source of inspiration for the Indian Youth Day. According to the Ministry of Tourism, the theme for National Youth Day 2022 is "It's All in the Mind." Fourth question. Which year Hyderabad was officially declared as the capital of Nizams? Option A 1769, Option B 1767, Option C 1758, Option D 1777. Your time starts now. The correct answer is Option A 1769. In 1769, Nizam Ali Khan Asif Jah II shifted the capital to Hyderabad. The 7 Nizams of the Asif Jahi dynasty ruled the Deccan for nearly 224 years, right up to 1948. In 1956, the Hyderabad state was divided on the basis of linguistic differences, and the city of Hyderabad became the capital of Andhra Pradesh. In 2014, the state of Telangana was carved out from Andhra Pradesh, and Hyderabad became its new capital. Fifth question. Which day is Telangana Language Day? Option A September 15th, Option B September 12th, Option C September 9th, Option D September 16th. Your time starts now. The correct answer is Option C September 9th. Telangana Language Day is celebrated on 9th September every year in Telangana, India. This date was chosen on the occasion of the renowned writer, poet of the Telangana, Kaloji Narayan Rao's 100th birth anniversary. The government of Telangana provides funds and awards for the improvement of Telangana. The Department of Culture organizes the day on behalf of the Telangana government. Sri Kaloji Narayan Rao from Warangal district wrote several poems, stories and novels about daily aspects of the common man's life. Kaloji Narayan Rao's Na Godava is the most famous among all his writings. Sixth question. Which company has made first ever PC using plastic waste in ocean? Option A HP, Option B Dell, Option C Intel, Option D Lenovo. Your time starts now. The correct answer is Option A HP. The leading computer manufacturer HP has made its first ever personal computer using plastic found in oceans.
Starting the session, there is another question. Let me answer that first. So, Pradeep is saying from Siddipet, my question, what is the difference between quantum computing and present computing? Okay, I sort of explained this when I said, answered the previous question, the advantages using quantum computing. Oh, yes. So these are the two questions, the new questions. So both are sort of the same question, and it is related to the answer I said previously. So the classical computers which obey classical mechanics, if we have computers which are the underlying laws are quantum mechanical laws, then we have certain advantages in certain computational tasks. For example, one is that prime number. For example, if you have okay, so as I have explained previously that quantum computer has certain advantages in computational task. So that's it. So if more explanations is needed for this, I will talk about that at the end of our session. So okay, so therefore I'm starting now. So now I apologize for now. Things will be a little complicated. So because there are a lot of theoretical jargons that we have to use now. So it is not now it's a little specialized discussion, the second part of my discussion. So it is also related to, we have to remember the things we discussed in the first session, my first session when I talked about linear algebra. So we are going to switch to that notation now. So for recapitulation, I'll say that about a vector. So a quantum state is represented by a vector called Kate vector in Hilbert space. So there is a dual space associated with every Hilbert space, which is this space of bra vectors, and this there are two sort of multiplication. One is this inner product, which we explained previously, and there is something called outer product. So this one, this vector alpha on the right hand side is the Kate vector, and this vector A prime on the left hand side is the bra vector. So this multiplication is called inner product. There is another product called outer product, like this one. These things we explained previously. So this, of course, here we will in any case recapitulate some of that when we talk about this. So is the screen visible properly? Can the handwritten thing can be written, read properly?
Sir, your screen is visible and handwriting is also visible, sir.
Okay, fine, thank you. So, okay, as I was saying on the previous session when we ended, that the observables that I was talking about a little ago, so are represented by Hermitian operators. Why? Because observables, from the nomenclature we cannot understand that observables are something which can be observed. So something which can be observed should be real. So the eigenvalues of Hermitian operators, which are basically the sort of, we can say, the values that we observe. So the eigenvalues of Hermitian operators are real. So that's why Hermitian operators are the operators which are the observables, which we can observe. So when you apply a Hermitian operator in the form of a square matrix that is applied on the Kate vector, which is the vector that is encoded with all the properties of a quantum state. So to extract that properties or to observe these properties, we have to operate something over that Kate vector. That something is the Hermitian operators, which are the observables. So I'm not going to discuss the proof of why Hermitian operators have real eigenvalues. So you know the proof, most of you probably know the proof, but I think most of you have a little exposure to matrix mechanics. So you know how to calculate the eigenvalues and eigenvectors of matrix. So if you know a little bit of matrix theory, you know that the eigenvalues of a matrix are, of a Hermitian matrix, are always real. So that is the proof here. I am not discussing that. So eigenkates are the base kates. What are the eigenkates? We have seen that the normalized eigenkate of certain observable, say a Hermitian operator, comma, complete orthonormal set. So what is complete orthonormal set? So let me recapitulate again. So what are these vectors? So the vectors are some elements on the particular Hilbert space. So Hilbert space has certain dimension. Let's say it is a two-dimensional system. So try to imagine the way you have understood the usual coordinate system. Say x, y, z coordinates are there. So three coordinates can be associated with three unit vectors like I cap, j cap, k cap. And any vector in that three-dimensional coordinate system can be expressed in terms of those I cap, j cap, k cap. So just extend that idea to a more general, much higher dimensional coordinate system. It can be 100, 1000, infinity, anything. So all for corresponding to all those dimensions, there has to be unit vector, just like we have seen in Cartesian coordinate system or polar coordinate system. Those are the eigenkets. So how can we know that they are sufficient to describe any vector in that any ket vector in that Hilbert space? So they has to be orthonormal first. Orthonormal means orthogonal and normalized. We talked about orthonormality before, but again let me repeat. Orthogonal is, so the inner product, let's say these A primes are the those unit vectors, that is normalized. It is norm is equals to unity, it's 1. So if we multiply, if we do the inner product between A prime and A prime only, then it is 1. But it is, if it is multiplied, I mean, do the inner product of A prime on some other normalized vector, say double prime, it is always 0. So those are called orthogonal and normalized. Complete means we have to take all of them. For example, technically what it is said, I will say in a few moments. So, but for the sake of understanding, let's say we are considering a three-dimensional system. So it's the three vectors are I cap, j cap, k cap. So we need all three I cap, j cap and k cap. So if we only choose say I cap and j cap, it does not form a complete set. Though they are orthonormal, it does not form the complete set. We have to take all of them. So therefore, how much orthogonal, many number of orthogonal orthonormal vectors are possible for a given dimensional Hilbert space, that is equal to the dimension of the Hilbert space. For example, if it is three-dimensional, so 3 such orthonormal vectors are possible. If it is 10-dimensional, not possible, there are them. 10 such orthonormal vectors are there. So to have a complete description of any vector in that given Hilbert space by these orthogonal vectors, we need to have all of them. So all of them completes the set, which is then therefore called the complete orthonormal set of vectors. So then any vector in that given Hilbert space can be described in terms of those orthonormal, complete orthonormal set of vectors. Just like here in the screen you can see some alpha ket vector is described in terms of these A prime vectors. So summation over A prime means it is summing over all the A prime vectors. So alpha, since A prime forms a complete orthonormal set, alpha can be written in terms of them. That's what we have done. Alpha is represented as sum over A prime, C A prime, A prime. So C A prime is called the coefficient. So what is that? Basically it is called the amplitude. So its modular square will give you it is a complex number in general. Its modulus square it gives the probability. Probability of what? So this alpha contains many of these A primes, say A prime plus A double prime, some coefficient into A prime plus some coefficient into M double prime, and so on. So what is the probability of occurrence of a particular eigenkate, that is A prime, in this kate alpha? That is given by the modulus square of this coefficient Ca prime. So these Ca primes are probability amplitudes, they are called. So they are associated with the probability of occurrence of the related or the corresponding basis vector or orthonormal vector. So how can we find the Ca prime? So if we do the inner product of A prime with the kate vector alpha, then what do we have? So basically in this equation, we are multiplying A prime from the left side on both LHS and RHS. So on the left hand side, we have A prime alpha inner product. On the right hand side, we have A prime over sum over all the A primes with this coefficient Ca prime. So now we know that this multiplication is linear. So Ca prime will be outside of the multiplication, and we can take the bra A prime within the set, within the summation, and we can have sum over A prime Ca prime is A prime inner product. So when A prime, the bra and kate are equal, since they are orthonormal vectors, they are equal, only then it gives you 1, otherwise it gives you 0. So basically it chooses on the right hand side, it chooses the corresponding coefficient Ca prime associated with the orthonormal vector A prime. So therefore this Ca prime can be written as the inner product of A prime with alpha. So if we now replace Ca prime by this inner product in this summation, we have the description of alpha like this: sum over A prime over alpha. So this, if we take this, single out this A prime thing. So first kate A prime and then bra A prime. Basically it is called a projection vector. Projection. So it typically picks only the A prime from the alpha vector. So it is just like we do projection in usual vector spaces. So you have a resultant vector. Consider xy two-dimensional vector. So you have an arbitrary vector on that. So there has two components to that, along the x-axis and along the y-axis. The axis can be chosen in any other way also. So there are the projection on the x-axis, which is the component of the result arbitrary vector along x-axis, and the component of this arbitrary vector along y-axis. This is same. The notation is different, but this is same, or we should say this is similar. So this A prime thing singles out the projection of alpha on different dimensions. Different coordinates, different bases. So that's why this A prime, which is called outer product, is also an operator which gives us the projection of the vector on a certain dimension, is called the projection operator. So this is on analogous to the vector projection that I just explained. So what is the completeness condition technically? Completeness condition is that if we, since A prime gives you a matrix, if we sum over all the A primes, it should be equal to identity. Identity in the form of matrix, that is identity matrix. So vectors, and these vectors, kate vectors and these operators are represented in matrix or vector form that I will explain later. If we sum over all of them, set of all the orthonormal vectors, it gives us identity. So that is the technical definition of this completeness condition I was talking about. If you only sum over all the possible kate vectors, then you get identity. If you do not get identity from those set of orthonormal vectors, then we can readily understand that these though they are a set of orthonormal vectors, they are not complete. This is the completeness condition. So this relation is known as the completeness relation. This product is called outer product. So it means usefulness of completeness relation can never be overestimated. So we can use completeness relations several ways. For example, this inner product alpha alpha, which is basically the modulus of alpha, the magnitude of alpha. So you see, since identity, if my identity matrix is multiplied with anything, any vector or any matrix, it gives a vector back. So since sum over A prime over all these outer products gives you identity, we can insert these within this product. And then we can do the product from the left hand side and the right hand side. So the left one gives you what? Alpha, the inner product alpha A prime, and the right hand side gives you the inner product A prime alpha. So they are complex number and they are conjugate to each other. So this is basically modulus of magnitude of mod of A prime alpha square. So each of them are basically probabilities of occurrence of A prime in the resultant vector ket vector alpha. So this is the sum of probabilities. See, if this alpha vector is normalized, so this total sum will give you 1. That is this, which is again basically sum of these coefficients square. Okay, so let us consider an element alpha, A prime, C A prime, A prime. So one of those elements. So that is C A prime over A prime. So that is basically which can be written like this: A prime outer product over the state alpha. We see that alpha selects this A prime selects a portion of the A prime parallel to A prime, alpha parallel to A prime. So that's why they are called projection operator, which I was just explaining. So if we represent this projection operator by this notation lambda, then sum over all lambda A prime is identity. So now let us understand the matrix representation of these vectors. Please excuse me. Excuse me for a minute.
Okay, sir.
For the interruption. So now the matrix representation. So as I was saying, these vectors, these case vectors are basically vectors, and these operators are matrices. So let us explain this notation then. So any K vector, so which is written like this, can be written as a column matrix or a vector like this form. And the conjugate bra vector is a row matrix with the complex conjugate of the elements of the K vector. So basically, what is the inner product then? So left hand side is the bra vector. So in the left hand side is the complex conjugate row matrix, and right hand side is the K vector. So right hand side there is this column vector. So you know how to do this matrix multiplication. So if you multiply these two, you get a number. That number is A star A plus B star B plus C star C and all that. So for taking inner product of a vector with itself, the terms are A star A plus B star B. So that means mod of A square plus mod of B square. So that is basically real quantity which gives us the magnitude of the vector. If we take the inner product with some other vector, say on the right hand side, this in the column there are A1, B1, C1 and all that. And the row there are A1, A2 star, B2 star, C2 star and all that. Then the resultant number is now A2 star A1 plus B2 star B1 and so on, which is in general a complex number, but a number all the same. And this outer product is what? On the left hand side you see you apply the K vector, on the right hand side it is the bra vector. So it is opposite. So first we have the column matrix and then the complex conjugate row matrix. Then you know by matrix multiplication rule, this gives you a square matrix. So if it is the dimension n cross 1 and the row is 1 cross n, so then it will be a n cross n square matrix. So that is basically an operator. So that's why this outer product is an operator acting on the vectors. So as we have explained before, this is called a projection operator. So these are the basic technicalities to understand the mathematics of quantum mechanics. So let us consider an operator X. So operator X, as you can understand, is a matrix. So let us now expand this operator in a particular through a particular coordinate system. So the coordinate system is here for the basis. So how to expand X in terms of basis? So let's say this A prime form a set of orthonormal, complete orthonormal basis. Now since X is a matrix, so if we multiply identity matrix of the same dimension both from left and right side, the outcome is again X. Because multiplying identity with any matrix or vector gives the matrix or vector back. So if we multiply identity matrix from left hand side and right hand side of this matrix X, it remains X. Now both of these identities, by using the completeness relation, can be expanded like this. On the left hand side, sum over A double prime, A double prime, A double prime, and on the right hand side, sum over A prime, A prime, A prime. Now they are the same basis vectors, but why we are writing A prime and A double prime? Because these are dummy indices. If we take only A prime on both sides, that is not right, because you know this rule from the matrix theory of matrix, that the cross term will then ignore the cross term. So to include the cross terms also, since they are dummy indices, we have to take other. So sum over A prime here, sum over A double prime. So I mean A prime, maybe if it is a little confusing, let's say I. So it's AI here and AJ. So I and J, this to include the cross term, this dummy indices should be different. So that is what, if we now do the multiplication, then we have the K vector A double prime on the left, and then we have some number, which is the inner product A double prime, the X operator acting over the over A prime. So this is the, please see my cursor, follow my cursor. So this is basically a number, and then the vector A prime. So what you have? A number associated with the outer product A double prime, A prime. A double prime, A prime means they are different, can be same. A primes are also exist, but different A prime, A double primes are also exist. So this gives you the elements, the position of a given matrix. And this number in between is basically the elements of that position. So if we explain this in a matrix form, how it will be? It will be like this. So this A1, these are the elements. So basically these elements are these A1 x A1 and then A2 x A2 and so on. And it is the conjugate element A2 x A1 and A2 A2 and so on. So basically when there is A1 and A1, they are the same, that is I is equals to J or A prime is equals to A double prime, they are the diagonal elements of the matrix. And when they are different, they are off diagonal elements of the matrix. But since this X is a Hermitian operator, that is an observable, so their diagonal element should be real and off diagonal element should be complex conjugate to each other. So the corresponding element, anti-diagonal elements. So A double prime x A prime is, we know that A prime x gather A double prime star. Now if it is a Hermitian matrix, so this is basically, we see from here that the cross diagonal elements are complex conjugate to each other for Hermitian matrix. So remember, even the matrices which are not Hermitian has their uses in quantum mechanics, but they are not observables. So this is how a vector or a matrix is expanded in this notation of bracket. So let us consider a specific example to understand it in a better way. Let's say we are considering the simple system of 2 dimensions. So A1, so therefore there can be only 2, dimension is 2. So therefore only 2 orthonormal vectors are possible in a complete set. So let's say one is A1, which is given by this
Sir, you are muted, sir.
matrix 1001. So A1 and A2 forms a complete orthonormal set of vectors. So they are basically the basis, can be understood as the basis. Now consider an operator, this sigma z. This sigma z is a specific operator called Pauli operator, Pauli z operator. The use of it will be, I will explain later. Right now just consider it as a matrix. So it is 1 0 0 minus 1. So it is a Hermitian matrix in fact, and it is also, curiously, it is also unitary. So this is a very unique example. So one matrix or a set of matrix in this case, there are others, 2 other like it, except identity. This is a matrix which is both Hermitian and also unitary. So identity matrix is the sort of trivial case which is also Hermitian and also unitary. But other than unitary, this is a very curious and case where these matrices are both Hermitian and unitary. But anyway, so what are the elements? A diagonal element is 1. So if you multiply this A1 sigma z A1, you see that it is 1. And if you multiply, you calculate this A2 sigma z A2, this is minus 4. So they are the basically diagonal elements, and we can understand that they are written in the basis of A1 and A2. Other elements are 0. So sigma z can be written therefore as AI, sigma z, AJ, sum over Ij. Well, these AI, sigma z, Aj are the specific elements. In this case, the diagonal elements A1, sigma z, A1 is 1. Then another diagonal elements A2, sigma z, A2 is -1. And the off-diagonal elements, they are 0. The previous example is a bit easy because A1 and A2 are basically the eigenvectors of sigma z itself. So sigma z is already written in terms of this A1, A2 vector. You see, you can calculate the eigenvector and eigenvalue of this sigma z. You will find that A1 and A2 are the eigenvectors with eigenvalue 1 and -1. So therefore, let us consider a different example. Consider, say, a Pauli matrix sigma x, another matrix which is again another Pauli matrix sigma x, which is this one, 0, 1, 1, 0. So for the expansion in the basis 1, 0, so A1 sigma s A1 is here, you can calculate this 1, 0, the matrix, and then 1, 0 column vector, you see that is 0. And A2 sigma x, A2 is again 0, and the off-diagonal elements are 1. So that is fine again because sigma x here is expressed in terms of this A1, A2 basis. Now let us consider a different basis, is plus and minus. So the plus is what? A1 plus A2 by root 2, and minus is what? A1 minus A2 by root 2. In vector form, this is 1 by root 2, 1, 1, and 1 by root 2, 1 minus 1. It is easy to check that this plus and minus are also orthogonal to each other and normalized, and they form a complete set. This is easy to check. Please check this in your at your leisure. You will find. So therefore, plus minus also form a basis, a different basis than A1, A2 in that Hilbert space. So now if we do the elements of sigma x in this plus minus basis, we find it is the diagonal elements for it will be plus sigma s plus. If we do this multiplication, we will find that plus sigma s plus is 1 and minus sigma x minus is -1. And the off-diagonal elements are 0. So this sigma x matrix, which was in the basis of A1, A2, which was like this one, 0, 1, 1, 0. In the basis of this new plus minus basis, this exactly looks like the sigma z matrix previously, which is 1, 0, 0, -1. That is also understandable because this plus minus orthonormal set of
Sorry, your voice is breaking, sir.
Sir, this is Rupan Das, is quantum mechanics, is the physics of the small. If you then in case yes, in case for non-linear okay, you see, everything small means you have to understand the scale of small. So what is small? So to us, macroscopic objects and people, to us, needle is small. Right, a needle is small. Ant or any other insects, they are very small. Even viruses or microbes, they are so small that we cannot see them. But at a quantum level, they are not small. Because, for example, microscopic dimension, for example, if you know the dimension micrometer or something. So that is what? That is 10 to the power minus 6 meter. So that is 10 to the power minus 6 means 10 lakh. So 1 by 10 lakh of a meter. So that is very small compared to us. But the dimension or the diameter of, say, a nucleus is the order of 10 to the power minus 14. So from the perspective of 10 to the power minus 14, 10 to the power minus 6 is 10 to the power 8 times bigger. So you see, though those things are smaller from our perspective, from a quantum mechanical perspective, that is not small, because quantum mechanical small is much more small. So this LC circuit and whatever you are talking about, so they are, I mean, the basic physics of superconductivity, of course, again quantum mechanical, but that is the underlying thing. But the LC circuit or whatever we are talking about, they are small from our perspective, not small from a quantum mechanical perspective. Just try to understand the computer you have, your mobile phone you see, or a new sort of this intelligent watch that we have, which are also computers. So the elements of them are small compared to us. So does they obey quantum mechanical law? No, because from a quantum level of dimension, it is not small, it is big, it is macroscopic. So please understand what when we say small, what do you mean by small? So it is relative. Small is also relative. So the quantum mechanical small is at the level of 10 to the power minus 12, 13, 14 meter. Okay? Hopefully I have been able to answer your question. So let me move on. Okay, so sigma x over plus, that we explained. So now you can understand how it is, the technicality of it is done. So let's say matrix multiplication. So can we reproduce the rule of matrix multiplication in our notation? So let's say Z is a matrix which is a multiplication of two other matrices X and Y. So the elements of the Z's is basically this inner product A double, say all the matrices are expanded in the orthonormal set of vectors A prime. So these are the elements of the matrix. So that is this inner product A double prime, Z A prime. So Z means we have what? Expand Z, which is A double prime, X, Y, A prime. Now we again use this very useful completeness condition. So between X and Y, we can insert an identity matrix I. So that identity matrix I can be further expressed as a sum over A triple dash, the outer product A triple dash, A triple dash. So therefore, this now becomes sum over A triple dash, this A double prime, X, A triple prime, Y, A prime. So you see now what? These are the elements of X matrix. And these are the elements of X, Y matrix. So if this is Zij, that is basically sum over K, Xik, Yk, So this is the matrix multiplication rule that we know from our matrix mechanics. So the rules of matrix multiplication can also be reproduced in our notation. So let's say now examine how Ket relation exists. So some Ket vector gamma, if we apply some operator X over some Ket vector alpha, let's say we get the resultant Ket vector gamma. So gamma is equals to X alpha then. So the inner product A prime gamma is basically the elements of the matrix. So what is that? So A prime gamma is basically A prime over X alpha. So A prime over X alpha, again insert the completeness condition between X and alpha. Then you have sum over A double prime, A prime X double prime, A double prime alpha. So this A prime gamma are the elements of the matrix gamma. So that is this column matrix, A1 gamma, A2 gamma and all that. And alpha, this A double prime alpha are the elements of alpha matrix, that is like this one. So therefore, this is the matrix multiplication, a column matrix into equal to a square matrix, which is this elements over again a column matrix. So that is again the rule of matrix multiplication that we can reproduce from our calculations, from our new notation. So what is this inner product? Again, inner product is B alpha. Again, we use this completeness condition. We have A prime, B A prime alpha. So that is basically the row matrix, A1, B star, A2, B star and all that. And the column matrix, A1 alpha, A2 alpha and all that. This gives us this summation. So basically, this is again the matrix rule that we can reproduce here. So, and similarly the outer product. Outer product is, say, the outer product beta alpha, which should be a matrix. What is that? Again, we use the this completeness condition. You see, this completeness condition is used so many times in this. So it is in our calculation. So it is an extremely useful relation. So you use that on the left side and use that on the right side. Then you have what? A prime, this number A prime B, alpha A double prime, then again the bra vector A double prime. So these two inner products are the multiplication of the numbers that are the element of this matrix. So if we write it in a matrix form, we have A prime beta and A alpha star, A prime A1 beta, A2 alpha star and so on. So these are the basically the elements. So I hope this technicality is understood. Let us now again consider a small two-dimensional system which is called spin-half system to explain further what you understand. So we are now going to consider one of the most important and elementary systems in quantum mechanics. The smallest possible system that can be considered in quantum mechanics is the spin-half system, which is the smallest Hilbert space possible, that is a two-dimensional space. This A1 and A2 vectors that we are talking about is, in our notation, it is written as 1 and 0 vector. So one vector is this 1, 0 and 0 vector is this column matrix 0, 1. So in the language of physics, they called energy eigenbasis for sigma z in fact. So in the language of quantum information, we call them this basis as the computational basis. There can be other bases also, as we have seen this plus minus basis and all that. But this basis that we usually use, which is the eigenvector of this sigma z matrix, which is called the computational basis. So the identity operator is basically the completeness condition sum over alpha alpha alpha, which is 0 0 plus 1 1, and the Pauli sigma z matrix can be written in terms of these as h bar by 2. We can also ignore h bar, so usually we don't consider h bar, so only this multiplication thing. That is, if we do the difference of these outer products 1 1 minus 0 0, we get the sigma z Pauli matrix 1 0 0 minus 1. So these are the eigenkette relations. So sigma x, since this is eigenvalue equation, 1 and 0 are the eigenkettes of sigma z. So if we apply sigma z over 1 or 0, we get the eigenvalues back, 1 and minus 1. So h bar by 2 is why, because we have considered this matrix with multiplication h bar by 2, but you can ignore h bar by 2 in general, because we can also consider h bar by without h bar by 2. So there are some other operators. For example, I was talking about there are the usage of operators in quantum mechanics which are not Hermitian. Just like this sigma plus and sigma minus operator. Sigma plus, again you can ignore the H bar thing. Sigma plus is basically, again it's a projection, but projection from one state to another. Basically this 1 0 means it takes the 0 state to 1 state. And sigma minus means it takes the 1 state to 0 state. So it is a sort of a ladder thing. From ground state to excited state 1, 0 to 1, and the vice versa, that is the excited state to the ground state 1 to 0. They are not Hermitian operators. So they are not observables. We cannot observe these sigma plus or sigma minus experimentally. But this sigma z can be observed. Why? Because it's a Hermitian operator, and Hermitian operators are observables. The sigma plus sigma minus are not observables. So the Pauli operators I was talking about are these three operators: sigma x, sigma y, and sigma z. Sigma x is this one 0 1 1 0. Maybe you will remember because this we used before. Sigma y is 0 minus I 0. Sigma z is 1 0 0 minus 1. These 1 and 0 vectors are the computational basis, which is basically the eigenvectors of sigma z matrix. And the sigma plus and sigma minus we just said can be written as sigma x plus I sigma y. I is the imaginary number 2 to the power minus 1, and sigma minus y is sigma x minus I sigma. So they are conjugate to each other, sigma minus and sigma plus. So what is measurement? Measurement means now we are talking about something that can be understood, experimentally realized. So as I talked about before, that the quantum mechanical states can be the state vectors are encoded with all the informations of that particular quantum system. Now, how to extract those? We need to do some measurements, some operations over those quantum mechanical states. So these operations of these measurements, they have a certain rules. So this is not like classical. This is again different from classical mechanics. So through this observation, we can take the information out of the K vector. How to do that? So what is this measurement? A measurement is a disturbance happening on the system and picking something up of that. So Dirac said it that a measurement always causes the system to jump into the eigenstate of a dynamical variable that is being measured. What is that? Let us elaborate. So let's say you have a K vector alpha. We expand these in the basis of A primes. A primes are the eigenkets, or the basis of so alpha contains in all those information, which can be written like this. Now we want to extract some information. So that will throw the system into one of the eigenkets of A prime. How? Because if we do the observation, let's say we consider a projection operator A1 over a quantum state Xi, which is written as this AI as I was talking about. So if we do this observation A1 over this Xi, we get what? CA1 A1. So the total thing was the sum or superposition of all those AIs. But this operation, particular projection, that is measurement, projective measurement, this is called, picks one of them. All the other are discarded. So this is why a measurement over a quantum system disturbs the quantum system. It makes it to jump in one of them. So measurement fundamentally changes the quantum system that has been measured. So this is something really very extremely different from classical mechanics. So you understand this is something like this. So let's say there is a door and somebody, I mean your door of your home, your flat, say. So somebody is, knocking on the door. So you expect three guys to come, one of the three guys to come. So when you are in your home and somebody is knocking, so from your perspective, any of the three is possible. So we can say that it's a possibility between all three, or a superposition between all three of them. But when you opens the door, you find one of them present. So others are discarded. But this is not fundamental. It is your ignorance. Because the door was closed. And though you from your perspective, any of them were probable, actually there was only one person standing outside the door. Why any of them are probable to you? Because you didn't know the full information about the system. It is your ignorance that you are describing everything in a probabilistic way. One of them is there. But that is the difference between classical to quantum. Let's say there is a quantum particle outside the person outside the door, if it is possible. Let's just, for the sake of the discussion, say, and this door is in between and this knock happens. This opening the door means this measurement. And after the measurement, you will find one of the three. But quantum mechanics says actually, when the door was closed, there was actually, it is a superposition of all three possibilities, all of those three possibilities. It is not your ignorance. It was actually such. Opening the door is something like a measurement which collapses the superposition of all of them to only one, which is explained by this measurement thing. When we do this P over xi, we get one of the AIs, that is A1. With a probability, how can we get the probability? We take the inner product of xi on left side and take the mod square, which gives us mod of C1 square, since this was the associated probability. So this actually happens. So this is the difference between classical and quantum, and this is how measurement is understood. So sigma z, I mean, now it is a little more explanation. Technicalities, I am ignoring this because I want to talk something else also. So what is expectation value? Expectation value is the thing that we acquire in reality. What is that? So expectation value is defined like this. So take a vector A, expectation value over the state alpha of this, of this operator A is this inner product alpha A alpha, where these alphas are normalized. If it is not normalized, then generally it is written like this, alpha A alpha by the inner product alpha alpha. So if it is normalized, then this inner product alpha alpha is 1. So this basically reduces to this representation. Expectation value is not eigenvalue. Why? Because it will be eigenvalue when alpha is the eigenvector of this operator A. Otherwise, it is not. So if we do say sigma z, okay. So if we do xi, that is inner product is 1. Say let's say xi is alpha 1 plus beta 0. So if we do this inner product xi over alpha, we get what? We get this one, which is not eigenvector. So this is what xi we write is like this: alpha star 1 bra plus beta star 0 bra, the sigma z matrix, and then the ket vector alpha 1 plus beta 0. If you calculate this, you will find that it is mod alpha square h bar by 2 mod alpha square h bar by 2. So this gives us h bar by 2, but this is not eigenvalue. This is different from the eigenvalue. So in a general expression, it is like this. Say alpha is sum over a prime c a prime a prime, which can be written as sum over a prime alpha. Let's say A primes are the eigenvalues of these eigenvectors of this Hermitian operator A. So this expectation value alpha A alpha means sum over A prime A double prime. So alpha A prime is now we expand A prime in the matrix notation. That is A prime A double prime A prime A double prime, and alpha is multiplied from left and right. So here we have what? Alpha A prime and A double prime alpha. So A double prime alpha, as you know, is the corresponding CA double prime, and alpha A prime is the conjugate, so it is CA prime star. And these elements are A prime, A small a prime, A cap operator, A double prime. So this is sort of a general expression of this expectation value. If it is not normalized, if alphas are not normalized, so there will be something like not CA prime square in the sum over that in the denominator. So, but we are considering them to be normalized. So let us explain again with spin half particles. That is two-dimensional system. That is again, before proceeding again to understand the whole thing, let's say 1 and 0 are the eigenstates of the Pauli operator. Let us say now we consider the quantum set plus. Plus is what? Plus is, as we have said before, 1 plus 0 by root 2. So this inner product 1 plus E and 0 my plus will be, you can calculate easily the these properties. Okay, I am not discussing it. Okay. So one thing that I wanted to discuss is, at least I should discuss the Heisenberg uncertainty principle before concluding this. So uncertainty principle we talked about before. Let us just conclude everything, this initial discussion, a session on quantum thing, with this proof of this uncertainty principle. So given an observable A, let us define an operator delta E, which is the observable A minus the expectation value of A. But this expectation value is taken for a certain physical state under consideration anyway. So this delta A square, which gives us basically the uncertainty, so that can be understood like this. So if we take the expectation value of delta A square, that is again delta A whole square, whose expectation value, that is A square, expectation value of A square minus twice A in this expectation of A plus expectation A square. So these expectation A are already expectation values, so no more averaging over them should be done. So only we have the averaging over A square, so that is we have, this is A square average minus twice average of A square plus A average square. This gives us average A square minus A average A square. This is something in statistical mechanics is called variance, root over of this. So this gives you the error of certain measurement. So this is the error in measuring, root over of this is the error in measurement in delta A square. Similarly, there is another, we can calculate these in different matrices, and the uncertainty relation in this notation, this term, is to say two incompatible observables A and B. If we take, and we take this multiplication, which will be greater than equals to 1/4 of the average square, mod of average square of the commutation of these two observables A and B. Where, so you see when A and B are compatible, that is they commute with each other, then their commutation is zero, so then there is no uncertainty in measuring in A and B. When they do not commute, like position and momentum or something, they have an uncertainty in their measurement. So to prove this, we need the Schwarz inequality that we have already proved, which in vector notation is like this bracket notation: alpha alpha beta beta is greater than equals to mod of alpha beta square. So to prove, here is basically the proof of Schwarz inequality given again, which I have already discussed, so I am not doing that. And the second important thing that we need is the expectation value of Hermitian operators are real. And the expectation values of anti-Hermitian operators are purely imaginary. The proof of it is I am leaving up to you. So let's say now we consider the ket alpha, which is this operator delta A acting over some blank ket, and ket beta, which is again this delta B acting over another blank ket. So therefore the alpha alpha inner product, we can very easily say that it is the average of delta A square. That is basically the uncertainty, square of the uncertainty of the measurement A. Similarly, beta beta is square of the uncertainty of measurement B. And alpha beta can be understood like this: mod of delta beta. So this measurement of this one, the blank delta A delta B blank ket, which is basically average of delta A delta B. So the Schwarz inequality says what? Alpha alpha inner product into beta beta inner product is greater than equals to mod of inner product alpha beta square. So therefore, using this, we have this left hand side del A square average into del B square average is greater than equals to average of del A del B mod square. Now del A del B can be written like delta A delta B minus delta B delta A by 2 plus delta A delta B plus delta B delta A by 2. So which is half of the commutator of delta A delta B, which is A minus A average A commutator of that, which basically reduces down to commutation of A and B itself. And it is the anti-commutator of delta A delta B, which is basically delta A delta B plus delta B delta A. So we can check very easily that the second quantity in the right hand side is Hermitian, and the first quantity in the right hand side is anti-Hermitian. So now if you take the average of that, so basically the first term is the average of anti-Hermitian, so that is purely imaginary, and the second term is the averaging of Hermitian, which is purely real. So therefore, this multiplication, this right hand side, that is average of delta A delta B square, is first average of the commutator AB square plus the average of anti-commutator AB square. Now since this second part is always real and positive, so a mod square of that is positive. So if this is equals to this plus this, the second term in the right hand side is a positive quantity. So this left hand side is greater than equals to 1/4 of this mod of commutator of AB square. So now we know that by Schwarz inequality that delta A square average, delta AB square average is greater than this average of delta AB square, which is in turn greater than this 1/4 mod square of the Heisenberg's uncertainty relation. So I'm sorry. So we needed to talk about something more also. But this is what we can discuss up to now. So I'm concluding my session with the explanation of Heisenberg's uncertainty relation. Okay, so let me go to the, I'm now go to the questions. So there are 3 questions, I guess. I think last one, Upan Shah answered. LC circuit is a lot. Yeah. This is Srinish. So the question of Srinish is, what does quantum mechanics tell us of teachers? Well, that is what I am talking about for the last more than 2 hours. So I hope you get from the talk, and if not, then later from the YouTube video. And the next question is there any research possibilities quantum computing? Yes, there are absolutely many research possibilities in quantum computing, both in India and outside. So you have to go through some exams and all that. If you want to know more about that, you can mail me later. So of course, even in Hyderabad itself, there are institutes who is doing research in quantum computing. One of them is our institute, that is IIIT Hyderabad. Okay, so if you want to know more, you can mail me later. So third one is Avinash. What is the biggest challenge in quantum computing? So there are many big challenges. One of these is I just talked about, that experimental realization, or to make a good quantum computing device, so a quantum computer. So the biggest challenge is sustainability. That is to make a stable quantum computer on a big scale. So there are some people have done with 50 qubits, 70 qubits, I guess, and more than that right now probably. But for the efficient working computer, as we understand, we need much bigger than that. So people are trying. There are some things that already we have, but in a much bigger scale, the sustainability to sustain a quantum computer is probably the biggest challenge in this area of research. Hopefully, yeah, this concludes all the questions. Do I have any other questions?
Priyanka Garu, I hope, are there any questions? Would like to really congratulate, and we're really happy for your session, sir. Thanks a lot.
Thank you, intern, to you also for giving me this opportunity. Thank you very much.
Sure. Thank you, sir.